Už to ide.
Dobre, je to vidno? Menia sa tam pluska? Dobre, Andrej, díky.
Ja som teraz nevidel.
Je to vidno? Menia sa tam pluska? Dobre, Andrej, díky.
Počul som nejakú ozvenu, neviem, či z YouTube alebo skadiaľ.
Spravedlne, niekto si púšťal YouTube. Dobre, ideme po anglicky, predpokladám.
Dobre, tak myslím, že už môžeme začať, nie? Funguje všetko. Ja pozerám, či sa niekto neprihlásili, tak musím si toto prichystať. OK. So, I would like to welcome everybody for our today's session. We are online from Institute of Physics. Today we're starting colloquium or the first colloquium from our institute. Next colloquia will be continuing. We hope that each month we can invite some interesting speaker who can talk us about his work and his achievements. Our first speaker is Dr. Nagai from our institute, and he tell us something about finding sign in Monte Carlo quantum algorithms. Some technical details at the beginning. If you have any questions to discussion, you can ask them through Zoom. If you are looking on YouTube stream, you can write them to the discussion or by email to me. Email is eric.bartosz@sauba.sk. And I think that we can start the talk, and other questions and remarks will be in discussion, following discussion. So please, I give time for our first speaker. So Dano, you can continue.
Thank you, Eric, for the introduction. And today I'm going in this colloquium, I'm going to try to explain to you why simulating and optimizing quantum systems is difficult, and what can we do about it, specifically in the technique known as quantum Monte Carlo, and specifically in the obstacle that comes up very often for quantum systems that's called the sign problem. What I want you to learn today is that there is a clever technique for simulating quantum systems called quantum Monte Carlo. There's a big obstacle to why it doesn't run smoothly. It's called the sign problem. That there is a numerical recipe for making it better and running easier that we have come up with. And there's a complexity result that in the end, it's still not too good. It's still hard in the worst case. I'm going to spend about 10 minutes on each of these things. And this is a joint work with Dominik Hangleiter, Ingo Roth, and Jens Isaac from the Freie Universität Berlin, and has been published in Science Advances last year. So here are the four things: a clever technique, a big obstacle to why it's not running well, our recipe for making it better, and then in the end, the result that it's still hard. So there are many clever techniques for dealing with quantum systems, with optimizations and going around problems. Some of these, the reasons why simulating quantum problems is hard is that in classical systems, our goal might be to find a ground state, find the ground state of using spin glass, find an optimal configuration. This can be still hard because it can include hard problems in classical optimization. But for quantum any-body systems, doing simulation and finding and optimizing the state of a system can be done fully only on a few sites. And when you want to do it in general, it's very, very hard. There are some low entanglement ansatz that people use, for example, Andrei Gengar and Roman Kuchma and their DMRG and CTMRG methods that they use here in our institute, but we cannot do it in general form. The goal that we would want in optimizing and simulating the systems, for example, would be to find the low temperature properties and understand the phases of matter. So why is it hard? When you want to simulate a quantum spin system, we are dealing with a huge state space. Classically, the state of a system is described by a bit string, while quantumly, it's described by a complex vector that has an amplitude for each of the possible bit strings that correspond to basis states. And then it's so that even describing a system, you need 2 to the n amplitudes that are complex numbers when you're dealing with a system made out of n qubits and 2-level systems. So the state space is huge. Not only the state space is huge, but when you want to do something about the system and describe how it's evolving, you need to deal with the huge matrices that describe that evolution. Even though they are built from small ones, the results are huge. So the evolution is difficult to simulate. To understand what we are getting in the end, to understand observables, is again a tough numerical task. And sometimes we would want shortcuts to understand the eigenstates of these matrices. Diagonalizing the matrices is also difficult in general. So you would ask, is quantum then difficult, more difficult than classical? And we would want to say it in complexity terms. So we want to say something that is provably more difficult than classical. There are 2 games that generally people play about this, showing that quantum is difficult. If any of you at the Institute know these games, I would like to play them with you. The rules are interesting. This is the Chinese chess. It's been from Vietnam. This is Baduk or Wei Qing or Go. This is a photo taken in Korea. So if any of you play these games, I would like to play with you. It's a lot of fun. So the 2 games that people play in showing quantum supremacy, or quantum advantage, that quantum systems are really harder than classical. One of them is random circuit sampling, played by Google, where in the superconducting circuits, they are applying random quantum gates, random quantum operations, and then looking at the output. And they're claiming that getting the output of the circuit gives you results that are hard to simulate classically. So this is not a useful task. This is just putting on random operations and looking at the output, which is a task that we can do quantumly. They do it with 53 qubits and 20 rounds of gates, about 1,000 operations. And there's a complexity result saying that if we could simulate this classically, this would be something really, really strange would happen in complexity theory. The second type of game that people are playing is called boson sampling. This is done, the first one was done John Martinez group at Google. This second type is done generally, most recently, most powerfully at the group of Pan Jianwei at the University of Science and Technology in China. And the game that they play is that they put individual photons on the inputs of a large array of beam splitters. And again, they are looking at statistics on the output of the system of indistinguishable photons. And again, there's a complexity result that says that if you want to classically simulate the output of this pretty much random circuit, and random interference pattern of individual photons, for this, you would need to be able to estimate permanence or do some other crazy task in classical complexity. This type of quantum advantage is also investigated by our group as part of our quantum project. So then there's a minor part. All of these things in quantum supremacy lie on that like the outputs of a quantum system somehow have some structure that is hard to come by classically. And in the end, if you want to come up with it classically, you would have to estimate some really, really difficult path. So it is very unlikely that you will be able to classically do it. So we were talking about that that it is hard to simulate quantum systems in general, in the worst case. But what do we do in practice? In practice, there's a workhorse that we use very often. It's called Quantum Monte Carlo. Here in our institute, it's what basically people in the OKFS group of professors use every day. It is used to investigate thermal and ground states of quantum many-body systems, to estimate expectation values, and it's based on a classical numerical sampling algorithm that samples from world lines in d+1 dimensions, the d-dimensional quantum system. I'm going to tell you a little bit of how it works and where is the problem applying it at a large scale for quantum systems, and why a lot of work is used when going around this obstacle. So the world-line quantum Monte Carlo approach is an extension of the partition function, where if you want to calculate the partition function for a system with a given Hamiltonian H, I'm going to extend this partition function, this huge trace that involves an exponential of a Hamiltonian. I'm going to divide it into many little pieces, put them out, and then each little piece is basically a transition from one state to another, calculated by some transition matrix. And when you look at what's happening here, how you calculate this Z, you can interpret individual terms as probabilities because they are positive for classical systems. And then calculate expectation values as looking at the values of observables for given states, like for going from one state to another state, with a probability that's calculated also from this formula. So in some sense, we are able to estimate expectation values by first recalculating some probabilities. And to calculate those probabilities, it is enough to run a particular randomized process, a Markov chain, that ends up with pretty much a typical path. And then if you do this many times, then you can figure out what the probabilities are, and then calculate the observable by multiplying results of this lambda with a probability and estimate them. This is nice, except we don't really know how long we need to run this process so that it has converged. And some difficulties can also hide under the surface. But it gets even more difficult when you go to a quantum system. But first, for classical, one more time, I'm just going to illustrate it. You can calculate the probability of a transition of going from a state lambda 1 back again to a state lambda 1 through many small transitions in the system that are taken from the off-diagonal terms in the Hamiltonian, pretty much. And we need to take this sum through all the possible paths. Again, you cannot take it through all the possible paths, but you need to take it through as many paths as possible, and you want to take a typical path. And for this, we go in the randomized process and try to converge to a typical representative. So this is quantum Monte Carlo as it runs. But for quantum systems, it runs into crazy obstacles. So what are they? The main obstacle for quantum Monte Carlo, for quantum system, is the sign problem. The sign problem comes out like this. When you're calculating these probabilities in quantum Monte Carlo, now the transitions in the Hamiltonian between different states are no longer just positive numbers, but they can be complex, but just even for simplicity, they can have varying signs. When you vary the signs of these Tn elements of Tm, the A alpha that comes out is not necessarily always positive, which means that you cannot interpret it as a probability and use your machinery for Markov chains as before. You can only interpret it as a quasi-probability because it can be positive and negative. So is this bad or not? Let's look in. So now we have these non-positive weights The expectation values are calculated with these non-positive weights, so quasi-probabilities. We can redefine these quasi-probabilities into probabilities by taking absolute values and redefining observables. When you're calculating like something with a Q and O, if I take an absolute value of Q, then I need to put the sign into the O. So I redefine observables. This is again doable, and we are trying to use the same machinery as before. But trouble comes in. Trouble comes in like this. The sample complexity, or how many samples do I need to take to get a good estimate, grows if the average sign gets smaller. So the variance grows with the inverse average sign of the elements Q. This means that if the quasi-probabilities vary in sign a lot, their average sign can be very close to zero. And if it's very close to zero, then what it means for the variance, it grows like crazy, can grow exponentially in the system size, which means that we have really low precision. And if we have really low precision, we need to take many samples. We need to wait a long time to even get every sample so that it is good. And that pretty much results in very, very slow numerical method. And that's why we need to take a lot of effort to get good results for quantum systems. Okay, so this is the sign problem. The off-diagonal elements of matrices of the Hamiltonian are varying in sign, which results in quasi-probabilities instead of probabilities in this quantum Monte Carlo. When the sign varies, the average sign can be very small, and then the precision gets very small. How do people deal with the sign problem? To deal with the sign problem, there are certain tricks. You can understand the physics of the system and somehow make a transformation on it so that what comes out is a Hamiltonian that has only positive or only negative off-diagonal elements of in the same direction. So for example, when the system dimerizes, you understand how to divide it into some blocks of two, and suddenly everything becomes cleaner. Or in special cases, there are some special transformations like the Wigner-Jordan transformation, auxiliary field, or Majorana transformation. What we want to do in our work is a general approach. So to go forward and deal with the sign problem, at least partially, without special knowledge of a system. So we can apply it generally whenever I get a system, I get a Hamiltonian, I can apply our method. And what we want, that our method of improving the sign would be reasonably easy to calculate. Our goal is to transform a Hamiltonian that has varying off-diagonal signs into a Hamiltonian that is stochastic. Stochastic Hamiltonians have only negative off-diagonal terms, or zero or negative. This is an interesting class of quantum Hamiltonians. They are not known to be universal for quantum computation, but they do not have the sign problem because off-diagonal elements have the same sign. There's been a lot of work done on non-stochastic Hamiltonians. First, they are ones that actually get applied in quantum computers like what the DOA has in their superconducting annealing quantum computer. This contains all of classical Hamiltonians, so it already contains like the class of problems in itself when you're finding ground states to optimization. And then there are interesting complexity results about how this class of Hamiltonians seems to be harder than classical Hamiltonians, even though they have only non-positive off-diagonal elements. So let's see, can we turn every quantum Hamiltonian into a stochastic one? Very probably not. But we can do this for some of them. So if we could do this, so turn a Hamiltonian by some transformation into a stochastic one, would it mean that the problem would be easy from now on? This is not true, because even classical diagonal Hamiltonians can be difficult to deal with in finding their ground states, because classical optimization can be hard, like finding the ground state of a 2D easy spin glass is an anti-complete problem. Well, the motivation why we want to understand this. So where does the hardness lie? Does the hardness for quantum systems lie in transforming them into a system without the sign problem? So was it hard because of the sign problem? Or was it hard because there's some hardness inherently even after you get rid of the sign problem? Both of these steps can be difficult. And definitely has been some confusion about this in previous papers. So we wanted to sort this out. And then there were also quite a few other groups that were working on this, and we were competing a bit and putting out papers. Now we were just a bit late after people have done computations on this, but in the end we have been able to come up with the results that we published last year, and I will tell you about this. So the sign problem is basis dependent. When you have a Hamiltonian, I can transform my basis, and maybe the sign problem can go away. Is there a good basis? Is there always a good basis where the off-diagonal elements are non-positive? Definitely, because when you diagonalize a Hamiltonian, it's just diagonal. It doesn't have any bad off-diagonal elements. However, diagonalization generally is a non-local operation. So we would want to find a local basis transform to get it into a stochastic one. So can you do this? Can you find a local transformation that changes the Hamiltonian into quantum, non-stochastic off-diagonal elements that are positive and negative? Can you transform it always into a stochastic one that does not have the sign problem? Can you find it true? It turns out this is what the other people have done. A group of Barbara Terha in your class, and then people at the University of Southern California, and they have proven that sometimes finding a cure for the sign problem is easy, giving an algorithm, and they have proven that sometimes deciding whether you can cure the sign problem is difficult in itself. So even deciding can you cure it is a hard problem for certain classes of Hamiltonians. For example, for two local cubic Hamiltonians, for some classes, your class and and others have proven that it can be sometimes hard and sometimes easy. Sometimes showing a complexity result, and sometimes showing an algorithm for actually finding a local transformation that takes a Hamiltonian into a stochastic one without a sign problem. So what is the path that we took? Through this phase, we want to, of dealing with the sign, we want to find not a path to our goal directly, but a path that makes stuff at least a little easier. So instead of trying to cure the problem, getting rid of the sign problem completely, what we do is we search for at least some relief. So try to make the sign problem less prominent. So instead of having the average sign being near zero, we want to make it larger, and that again decreases the variance and decreases the need for taking many samples and so on. So we want to optimize the sign. This is difficult. So instead of optimizing the sign, we come up with a new way of dealing with it by optimizing something that we call non-stochasticity. So why easing the sign problem, so dealing with it, at least even partially, is difficult. So when I take a Hamiltonian and I transform it in a different basis, and I want to see how am I doing? I want to find out how my average sign, what my average sign is. So to calculate the average sign, I have to do the calculation that I have been doing before, but that calculation is difficult because beforehand the sign was bad. It was the average sign was very small. So that means that if I want to improve it, when I couldn't do it in the first place, I have to calculate it so that I'm running in circles. Because if I want to optimize the average sign, I cannot do it because I cannot calculate the average sign because it is infeasible in the first place. So we have to come up with something better. We don't want to calculate the average sign. We want to calculate something else. Okay? What we do, we minimize something that we call non-stochasticity. Non-stochasticity of a matrix is a measure that we define as adding up all of the positive off-diagonal matrix as elements. Now, when we do local transformations of the system, we can again relatively easily calculate this measure, which means that we can use it in our optimization. So basically, I do local transformations, calculate, I measure, and see whether I have done better or not, whether I have improved the non-stochasticity. So again, what we're doing is we're checking whether our local transformation is changing and improving the measure of non-stochasticity, which is the sum of all non-stochastic matrix entries, which means the positive of diagonal elements. And then we're minimizing it, so searching for the best local transformation that minimizes this non-stochasticity measure. Now, is it any good? Our results show that it is, that when we're for systems that we were able to investigate numerically exactly, or actually calculate the inverse sign by quantum Monte Carlo, that the inverse sign correlates pretty well with our non-stochasticity measure. This is done only for random 5-qubit Hamiltonian, so these are very small systems, so this is really just a proof of principle, and it does not always work, but it shows that it could work on average on some systems. Okay? So now we're claiming that optimizing non-stochasticity will improve the sign. Again, another thing that we investigate, we just investigate some toy systems that are frustrated ladders. So these are systems where you have something in 1D, on 2 layers that are connected, and the system is frustrated, meaning that like there is no easy way to optimize every local term by itself. So it is a complex system. And then we are looking at how much did the average sign get better if we improved our non-stochasticity measure. And a lot of the time, we really do get an improvement. So again, this is a proposal for a numerical method that I hope that somebody could implement on a large scale, because we are not numeric people. We are theorists that do not have a very good implementation of the quantum Monte Carlo that we would need for this, to actually see whether what we are getting by improving non-stochasticity actually really makes the running of the quantum Monte Carlo much better. And we will really welcome collaboration on this to see whether we could check it on an actual big system. So this was our proposal. Not cure the sign problem, but make it better by minimizing not the sign itself, but by improving the sign itself, but improving another measure, which was non-stochasticity, which was easy to calculate, because calculating the sign itself is hard. So you think that everything is rosy and flowery, and our method will be working, but the devil is in the details. There's something hiding in there, and what's hiding in there is the worst case scenario. So the worst case scenario that we are investigating is showing that even if you want to ease the sign problem and make it slightly better, in the worst case, if you could do this, you would be solving something that's too complex, or that it would be very unlikely to solve, because you will be solving NP-complete problems. So how do we arrive at this, and what does it even mean? So let me give you a very, very baby version of computational complexity. This is what I do most of the time in my work. I'm looking at what quantum computers could do and could not do, and how hard are different problems for them. But here, this is just classical. So the class of problems E is the class of problems where the answers can be calculated on your own. For example, is the Euler path problem. Look at this graph on the left and see if you can draw it with one line without lifting your hand. Yep. And you can solve this problem even if I gave you a really big graph. There's a technique of dealing with this. Or other interesting problems in this class is, for example, primes. So given a number with n bits, you can check deterministically with polynomial efficiency in the number of digits whether this number is prime or composite. Or other problems are linear programming, or finding the minimum cut on a graph, or maximum matching when you have a graph and you're trying to find maximum number of pairs that exist like on edges, so that every vertex has one edge coming from. On the other hand, the class of problems NP is the class of problems where you can take solutions and efficiently verify them. It doesn't mean that you can find the solutions, but you can verify them. For example, it's the Hamiltonian path problem that you have here on the right with the chess horse. The problem is that you have a small chessboard like this, and your task is to take the chess horse and jump all around this board, jumping on every side and coming back home. You already see that there are many options that you can take, and for a generalized problem on a big graph, on a big chessboard, this could be quite difficult. But if I told you the solution, you can verify it and check that it's okay. Here, I'll give you the solution, and you can see that all the moves are legal chess horse moves, and we have indeed covered the whole chessboard and came back to the same spot. So this is an example of a problem in the class NP. You can efficiently verify solutions to these problems. Examples of problems in this class are maximum cut, where you have a system, you have a graph with vertices and edges, and you're supposed to color vertices with two colors so that there are as many as possible edges between vertices of different colors. So you want to find as many as possible edges that have a one black vertex and one white vertex on the other side. You know this problem from physics as the antiferromagnetic easing model, or an antiferromagnetic easing spin glass if it's on in general geometry with many different interactions that have positive and negative values. Okay? So what we do in our work, we show that sign easing, so making the sign problem easier, is still hard in the worst case, because if you could solve sign easing, meaning that like you could improve the sign beyond some value, it would mean that you would be solving an NP-complete problem called max cut. So in the worst case, for when you have a Hamiltonian that's of the XYZ type, which means that there is like XX, YY, and ZZ type or interaction terms, it's too local in general geometry, and you're allowed orthogonal transformations of the system. If you're able to calculate our measure of non-stop plasticity and find it and decide whether it's below A or above some other value B, it will mean that you're solving max set or max cut, and that means you will be solving NP-complete problems, which means that that our problem is NP-complete. Because if I gave you a local transformation and claim that it reduces the non-stop plasticity a lot, you could verify it. Do the local transformation, calculate the non-stop plasticity, and see, yes, it is working. On the other hand, if you found that transformation, you would be able to solve other problems that are really hard by taking a max cut problem, transforming it into a Hamiltonian with a sign problem, and then asking if this sign problem can be improved beyond some value. So we are able to transform NP-complete problems and hide them as a sign problem that wants to be improved. And our result is interesting because it has fulfilled a hole in our understanding of a dichotomy, because for complexity problems called satisfiability, we know that two-sat, so figuring out whether you can satisfy all conditions for pairs of bits in a string, for example, saying that like this pair of bits cannot be in the 0,0 state and this pair of bits cannot be in the 0,1 state, and you have many conditions like this on a string, this can be solved classically. An analog of this in for the sign problem is that we now know that curing the two local Hamiltonians of the XYZ type, fully curing and understanding whether you can do it or not, and actually in the cases that you can do it, there is an algorithm for this. This is easy. or understandable now. On the other hand, so this is the result of our class and interval. On the other hand, for free satisfiability, when you're looking at strings and you are looking at, can I satisfy conditions that involve 3 bits at a time? For example, saying that these 3 bits cannot be equal and these 3 bits cannot be in the state 110. Finding whether there is a solution to all of these conditions is NP-complete. This is the famous result of Cook and Levin from the 70s, that 3 sub is NP-complete. So it is as hard as anything in NP. If you could solve it, you could solve everything in the class NP, which efficiently, which means that you could solve every problem whose solution is efficiently verifiable. On the other hand, for the side problem, if you have 3 local Hamiltonians, and if you could cure 3 local Hamiltonians and get rid of the sign problem completely, it would mean you would be able to also solve 3 sub, because you can transform 3 sub problems into quantum Hamiltonians with a sign problem, and then get rid of the sign problem would mean that you could solve the original 3 sub. This is the result of Marion and Lidar. And what we do is we find an analog of the dichotomy here, that there's a difference between 2 local and 3 local conditions. And on our side, there's a difference between 2 local and 3 local Hamiltonians. That the problem max 2 sub, which is asking, can you break only a few, or like below this number of conditions, not to satisfy them all, but to break below some number of conditions for 2 local conditions for bits on a string. In our case, we are asking, if you have a 2 local XYZ type Hamiltonian, and I'm asking, it has a sign problem, can I improve the sign problem below some value? If you could solve this, you will be solving max 2 sub, which means they will be solving NP-complete problems. So sign easing is hard for 2 local Hamiltonians in the worst case. Of course, it doesn't mean that our numerical method is bad. It only means that it won't always work. But we are really hoping that it will work well in some useful cases. Because there is an interesting connection that even though some problems are known to be NP-complete, there are good algorithms for their, well, sometimes there are, in some cases, good algorithms for their approximation, for making them, for not finding optimal solutions, but finding near optimal solutions. And near optimal solutions for a sign problem might mean that we could just take much less time to do the simulation, and we might be able to reach larger size problems, or just even get better precision that we need in our investigation of quantum many-body systems. So the problem that I have talked about, that we are transferring the sign problem into max cut, is basically an antiferromagnetic optimization. And imagine that you have a graph, and you have spins that can be up and down. And now we are asking to find the optimal antiferromagnetic configuration. So try to put spins up and spins down on the vertices, and have as many as possible have opposite directions if they sit on a particular edge. Oops. And then what we do, we map our sign easing into solving max cut. So we take a max cut instance and we create a Hamiltonian that somehow there is a 2 local of the XYZ type that cannot be eased unless you are also having like an antiferromagnetic configuration on the max cut side. So then counting the number of broken links on the max cut corresponds well to how much you're improving our non-stochasticity measure. And in the end, we show that the sign is NP-complete for 2 local XYZ Hamiltonians under orthogonal Clifford transformations and also general orthogonal transformations. And there's been a lot of mathematical work that mainly the students Ingo Roth and Dominiano have done. Right, so this is a bit of the paper, and skip this, and let's stop and reflect to see what I have told you about today. So I was trying to tell you how to ease the sign problem and improve the quantum Monte Carlo numerical method by reducing non-stochasticity. Quantum Monte Carlo is a fantastic method that is a go-to method today for quantum many-body systems, but it takes a lot of time because of imprecisions that come from the huge obstacle that is the sign problem. So we are giving a numerical recipe for easing the pain. That's one thing. And the second thing, we're giving a complexity result and showing that this problem, easing the sign, is still hard in the worst case. And now a little bit of the story of the paper, because there have been a lot of arguments about this. This is my PhD advisor, my wonderful teacher that I've had, Annie Farhi and Jeffrey Goldstein. So what's the history of the paper? So we have actually sent the paper to many journals until we got it accepted. And it's only because of the perseverance of my co-authors that we managed to publish it as well as we did. So here is what people have thought about this. People have thought that we are bundling together different and somehow opposing results, and that this is bad. But this is actually a feature. We are combining a numerical method and also showing that the worst case is hard, and there was a novel complexity result. Also, it happened that the referees did not understand what we were doing, because they were asking like this calculation is difficult. You cannot improve the sign. Like, well, what are they calculating? And half of the paper is like, we are not calculating the sign itself. We calculate the non-stochasticity, which you actually can do and calculate. Then we have dipped our toe into a huge area of numerical people that live by quantum Monte Carlo. And that means that we really are unaware of many developments and cannot possibly cite the tons and tons of papers that people would love to cite, to be citing. So that means that you just have to be lucky with the referees so that you cite the things that they want to be cited, because you cannot cite everything. And there really is a large body of literature that we need to learn and to understand of what's been happening recently. But it doesn't mean that what we are doing is obsolete or not doing anything new. And so in the end, we have been able to get through the referees on the 6th try, and you can say that we got lucky, or that we got vindication that what we did here is actually good. And we will see what you have to say about this, or then later discussions of whether we can actually apply this in any of those groups. Thank you for attention. This has been my IP SAS colloquium on tough optimization for quantum systems and our result from last year for aiding the sign problem.
Okay, thank you, Daniel. Now we can start a discussion. You can ask speaker, or you can make some comments or notes to his presentation. So please, you can ask.
This is Richard Hlubina. May I ask something?
Of course.
Daniel, so did I understand correctly that in your examples with your spin systems, you just made some kind of local basis rotations with your spins?
Right. So we can do local basis rotations, or we can do even more complex things that are then harder to calculate what has been done. But it's local transformations and seeing whether some local measure has been improved or not.
And if I wanted to apply this method to, say, itinerant electrons, where like something like a Hubbard model, would you have an idea how that local transformation might look like, which might be able to to reduce this stochasticity?
So I don't really know what are the details of your system, but just to give you an idea of what's happening, that we have local interactions, and then when I do a local transformation, that I can look at how each local term has changed. So that means I can calculate how much they contribute to the positive of diagonal terms. So if there's something of this type, where you can take your local interaction terms and then make some transformations on them, like the class that you are familiar with, that what's usually done for your systems, then you can do this calculation.
Yeah, the point is that
I think we need to sit down in detail to see what your interactions are and what.
Yeah, the point is
what
that
class of local transformations you could do.
in the case of a spin system, I can imagine that if I turn the spins in the right directions, then some minuses disappear or appear, whatever. But if the physical nature of the states locally changes very much, as in a Hubbard model, empty side, an electron present with spin up or spin down, or a doubly occupied side, for instance, in the Hubbard model, then these are very different objects. And it seems to me that it's not easy to, it doesn't really make much sense to me to mix those states. So I would imagine that the basis transformation would have to be at least non-local, at least it would have to at least involve two sides or something like that. Did you ever think about such transformations?
Yes, of course. So again, like if the transformations are just k local, where it's a constant, then you can do this calculation. Of course, to improve on more complex systems, you would definitely need to go to larger to transformations that involve a few sites. But as long as you involve not too many sites, then you can calculate what your transformation has been doing. I hope.
Well, even that might be not that completely easy, because say if I have a two-dimensional model, then the matrix is not diagonal. It has some very far away lying matrix elements, and they may change in very strange manner.
Yeah, there could be some crazy blow up. I don't have any good intuition about what's happening, but I would love to see.
Okay.
What's going on?
Okay, thanks.
May I have a comment?
Please.
To Richard. Richard, imagine a Hubbard model that you have like L sides. The dimension, Hilbert dimension of the system is roughly 4 to the L. If you make such a huge matrix for the Hubbard model, you will see that this matrix will contain both positive and negative numbers. And mostly this talk, very simply speaking, talks about the Hamiltonians which have only positive numbers. Okay?
Oh, I don't agree. The goal is to transform the Hamiltonian from one basis to another, and to make it more stochastic, no?
Yeah, but it's not a stochastic, it's something else. This is stochastic, if I remember well.
Yeah, it's just a mispronunciation.
Yeah.
No, it's really mispronunciation. I think that stochastic actually means something that the matrix elements are all positive, while stochastic is something very random.
Non-positive.
Non-positive, okay. Zeros then, okay.
No, with the mispronunciation, I thought that the Richard has meant stochastic.
Yeah, that's what I meant. Yeah, okay.
Okay, and for example, for Daniel, your system, is it possible that your, for example, wave function can be antisymmetric or not? This is a question to Daniel.
Yeah, I understand.
So by exchanging two particles, like the two spins, because this is very crucial for the Hubbard model.
Right. So again, like if the Hamiltonian has this symmetry, then what you're doing with the transformations should keep it. I don't see why it would not work.
Yeah. So I think,
but again, it is possible that we are coming that because of this, while we're writing local transformations, that what we're doing is that that necessarily, for example, they would improve something on one side and make worse on the other side. So they would be running in circles and not doing anything. It's possible that there are systems like this. This might be fine. That kind of.
Okay, thank you. Yeah.
So please, any other questions, comments? Maybe I can ask, at the end you mentioned some reports that are very similar to reports from referees to other papers of our colleagues, but I will return to the beginning. You mentioned some experimental setups as quantum programmable devices and these individual photons interactions for receiving quantum supremacy or so. What are other mainstream devices or techniques to use these Monte Carlo methods? Do you know something?
So
one
thing is that, like, what people actually do to build quantum computers and like to try to reach quantum supremacy, meaning that they have a quantum system that does something that the classical system doesn't do. That basically the two leading approaches now are superconducting quantum circuits that are actually universal. So if you had them, you could do anything that a quantum computer can do. While the other one in linear optics is not universal. It was a sampling approach. So that means it's only used to be like, oh, we're doing something quantum that you can do classically. But I did not quite understand what your connection to quantum Monte Carlo was. So with quantum Monte Carlo, you can simulate quantum systems, probably like the ones with the spin systems that are used in the superconducting circuits. That's what you could do, but again, only up to some limitation.
Okay. So, any other questions, comments, or notes? No. So I would like to thank you again. There are no questions. I can see no raised hands.
Okay. Have a good day and hope to see you in person. Things get better soon.
So thank you, everybody.
Thank you for the talk.
Our colloquium will be continuing maybe next month. We must get some new speaker, and we send you invitation again. It seems that we will be continuing online on the Zoom platform, so you will receive invited link for this session. Thank you.
Ahojte, dovidenia.
Thank you, bye.
Goodbye.